Okay, so we are happy to start this afternoon session with a talk by Minshan Zheng. He's going to talk about integrand for less-supersymmetric young males at one loop.
Okay, can I start it?
Yes, please.
Okay. First, thanks for the organizers for giving me this wonderful opportunity to share a recent work in collaboration with Jake Virgili, Enric Herman here in the audience, Cameron Langer, Kokimitis Pavtokas, and my advisor, Yaroslav Strinka, integrants for less supersymmetric young male theories at one loop. This is based on a paper that appeared yesterday. So amplitude methods has a lot of applications in physics problems of both theoretical and practical interests. We've heard a lot yesterday and earlier this morning on how amplitudes can be used to constrain the space of effective EFTs. And we've also heard applications of amplitude methods to the study of cosmological correlators, and later on a lot more on its applications to gravitational waves. In this talk, we'll be interested in an orthogonal direction, that is the formal aspects of scattering amplitudes, and with an effort to develop new methods of calculating scattering amplitudes and finding new structures in scattering amplitudes that deepen our understanding of quantum field theory. This morning, we heard an interesting talk on Feynman integrals. The object of interest in this talk will be loop integrands. It's useful to think in terms of loop integrands, not just for the calculation of loop amplitudes, but also because they provide an important starting point for exploring new hidden structures. We have seen enormous progress made in the study of planar n=4 super young male theories, and would like to know if there's any non-trivial interesting structures in super young male theories with Lex-Land maximal supersymmetry. And to this end, we will need more theoretical data. And in this talk, we'll focus particularly on one loop integrands for planar super young male theories with n=1 and 2. There are many ways to construct loop integrands. We can use the unitarity methods or the double copy relations or the amplitude twistor strings and so on. For this talk, our discussion would be in the framework of generalized unitarity. The basic idea of generalized unitarity is that we can construct loop integrands directly from gauge invariant onshore tree amplitudes. In practice, loop integrands are rational functions of loop momentum, so we can expand them in any sufficiently large basis of loop of integrands. And the coefficients are fixed by comparing the residues of our integrand expansion to the residues of field theory amplitudes, also known as cuts. And cuts are given by, from the principles of unitarities, they are given by products of tree amplitudes summed over states crossing the cuts. To express the integrands of amplitudes in a given theory, the size of the integrand basis needed is dictated by the space-time dimension and the power counting of the theory. The n=4 super young males has, in the context of integrand reduction, there's a very well-known classical result from Pastorino and Vellman for one loop, and in 4 dimensions, we know that any integrands, one loop integrands with more than 4 provocators can be expressed in terms of integrands with 4 or less provocators. And super young male theories, n=4 super young males in 4 dimensions has box power counting, whereas with Lex supersymmetry, the amplitudes at infinity will have higher power counting behavior. In particular, for n=1 and 2 in 4 dimensions, the amplitudes scale at infinity like a scalar bubble integrand. And so the integrand basis we need is one of scalar bubble power counting. We will need bubble integrands in addition to boxes and triangles. Now, to fix the rational coefficients, we need to compare the residues of ansatz to a spanning set of field theory cuts. Field theory cuts are product of trees, and they can be represented in terms of on-shell diagrams. The basic idea is we can further factorize everything into products of 3-point amplitudes. Just to set up the notation that we'll be using in the rest of the talk. So we will represent the cuts of field theory amplitudes in terms of on-shell diagrams. And the basic building block of the on-shell diagrams are those 3 particle vertices. We will indicate with a white vertices a MHV bar 3-point amplitude, and with blue vertices, we represent a MHV 3-point amplitude. For theories with for NLEX length 4 superyamules, we also need to specify the holistic configuration on the external legs that is represented by the arrows on the edges. Here we use an incoming arrow to indicate states that are connected to states that are connected to gluons with negative helicity, and outgoing arrows represent states that is connected to gluons with positive helicities. For given on-shell diagrams, with given external helicity configurations, there may be one or more allowed internal helicity flows. When there is only one allowed internal helicity flows, the diagrams represent a singlet cut. Whereas when there are multiple allowed helicity flows flowing internally, the diagrams represent a non-singlet cuts. And to compute the non-singlet cuts, we need to sum over all the contributions from different internal helicity flows. And here's just one example. And computing these non-singlet cuts in terms of the on-shell diagrams, we found this result, and this shows that non-singlet cuts generally has explicit dependence on the number of supersymmetry we have. By contrast, singlet cuts will be independent for any amount of supersymmetries, and in particular, they will be the same as the result from n equals 4 superyamules. Okay, enough for the notation. So now we fix those coefficients by a spanning set of field theory cuts. In one standard implementation of generalized unitarity, the procedure is the following. We can first fix all the box coefficients by looking at a set of quadruple cuts. After that, we can fix the triangle coefficients by a set of triple cuts, modulo removing the pollutions from the boxes. Here, the triple cuts are functions of one unfixed perimeters. So we can pick any one point on the cut surface to write down the equations. And similarly, we can proceed with the bubble coefficients by looking at double cuts and remove the pollutions from the boxes and triangles. Here there are, in this implementation, there are 2 levels of arbitrariness. One, we can start with an arbitrary basis of integrands, provided it has the correct power counting. And we can choose an arbitrary set of spanning cuts to match. The complexity of the linear algebra problem that we need to solve in order to fix the coefficients will depend on these arbitrary choices. And for bad choices, our coefficients can generally be arbitrarily complicated linear combinations of field theory residues. So despite this technical complications, in principle, the one loop n equals 1 and 2 integrands in 4 dimensions are completely determined by this standard cut analysis with one exception, that is the coefficients of massless bubble integrands. You may immediately ask, why do we even care to include massless bubble integrands in the first place? After all, these integrants integrate to 0 in dim-reg and has no effects on the integrated results. The reason is the following. This integrand integrates to 0 due to a non-trivial cancellation between the UV divergence and the IR divergence. And we could separate these UV and IR divergences by using a different regulators. And if we want to correctly account for the UV and IR structures of the amplitude, we will have to take these integrands into account. However, the cut topologies that we are supposed to use to fix the coefficients are problematic. Precisely, there will be two solutions to massless bubble cuts. Sending the first propagators to 0, the second propagators will factorize. So we can choose which poles to send to 0, and this gives us two branches of solutions. And for any amplitude of any holistic configurations, we will also always find one singlet configuration and one non-singlet configuration. While the singlet cuts are always well-defined and equal to the n equals 4 result, the non-singlet cuts suffers from collinear divergence of the multi-particle tree amplitude. And so the goal of this talk will be to find a cut level definition of the massless bubble coefficients. Before we actually get to solving these subtleties, let me take a technical detour to introduce a refinement of the cut matching procedure known as the prescriptive unitarity. The main purpose is to discuss the massless bubble coefficients as cleanly as possible without the pollutions from box and triangles. So the basic idea of prescriptive unitarity is that instead of an arbitrary basis, we can choose bases of integrands such that they are diagonalized in the spanning set of cuts we want to match. Here is the general structure of a prescriptive representation of one loop integrand. Every coefficient, the coefficient of every basis integrand is a single field theory residues of maximal codimension, also known as leading singularity. And the prescriptive integrand bases are by no means unique. In practice, to construct a prescriptive basis, we can start with an arbitrary basis for nx1, 2, that will be one with bubble power counting in 4 dimensions. And we will enumerate a spanning set of cuts we want to match explicitly, and then diagonalize the basis with respect to our choice. And here in our paper, we consider, this is the spanning set of cuts that we considered in our paper. They are chosen such that the resulting numerators will have nice properties, that the UV divergent terms and IR divergent terms are separated whenever possible. And instead of getting into the details of how to specify the contours and how to construct the numerators, let me just show a few explicit examples to give you a flavor. So here's an example of 2 box integrands. The contours, the defining contours for these integrands are very simple. They are simply the ones that you will use to, they are simply the ones corresponding to computing residues on the 2 solutions to the quad-cut equations. And the numerators here are written with these double line notations are constructed to be chiral. These notations indicates contractions of momentum written in terms of Pauli matrices. They can be written in terms of chiral traces that may be more familiar to some of you. The point is, these numerators by constructions will have support only on one defining contours with unit residues and vanish on the other. And the triangle's bubble contours needs a little bit more explanation. Note that triangle and bubble integrands unlike the box, have poles at infinity. This can be seen explicitly by parameterized loop momentum in some parameterization. And we can see that the triangle integrands, scalar triangles have a single pole at infinity, while a scalar bubble have double poles at infinity. And the point is, we can choose our defining contours for the cuts as such that they not only encircles a number of Feynman propagators, but also the poles at infinity. For example, for these one mass triangles, our contour choice will include sending three propagators to 0 and then encircling a pole at infinity. Actually, I shouldn't say one pole at infinity because we don't have a single pole at infinity, but a surface of poles at infinity. And I need to tell you how we approach the poles at infinity. And this is encoded in this projection condition where we introduce this null momentum px for reference. This reference momentum px will appear in the numerators we constructed, as well as the leading singularities we computed with these defining contours, but they will of course drop out of the final expressions of the loop integrands. And bubble coefficients are defined in a similar way. Here, let me gloss over the technical details. Suffice it to say that while it takes a non-trivial amount of work to figure out a nice defining set of contours and construct numerators, the contours are conceptually simple. And once we have constructed the prescriptive basis, the coefficients of integrands for any one loop amplitudes are straightforward to compute. You just evaluate the leading singularities on the defining contour. And with that, we will almost fix the loop integrands up to the contributions from massless bubbles. And in our paper, just for concreteness, we construct the expressions for one loop amplitudes, one loop MHV amplitudes up to all multiplicities, and for NMHV up to 6 point. Now we have settled every other coefficients. Let's go back to the massless bubble coefficients. Here we find two natural scenarios that give rise to two distinctive loop integrands. The first natural scenario is we can choose, there's only one single degree of freedom to match. So we can choose to match it with the well-defined singlet cuts, and then define the naively divergent non-singlet cuts, the value of the divergent cuts to be the value of the cuts of the local expressions that we constructed. And since singlet cuts are independent of the number of supersymmetries, and in particular, they are the same as the n=4 result, they should be free of poles at infinity. And this implies, in fact, that every massless bubble coefficients should be 0, as you can easily check that every other integrants in our basis have no poles at infinity on these double cuts, on the simulate double cuts. And so the only reasonable conclusion is that the massless bubble coefficients should be set to 0. And the result of implementing this, the integrand we get from this strategy differs from the standard results in the UV and IR structures. And the difference is exactly a multiple of massless bubble coefficients. There's a different scenario that is also natural. We can think of these problematic cuts as the leading singularities associated with these cuts as arise from a collinear configurations, the collinear triple cuts, and it would seem natural with this interpretation to define the values of these cuts to be the tree amplitudes. And if we implement this prescription, the resulting loop integrand will have exactly the same UV and IR structures as in the standard literature. So to wrap up, we have constructed one loop integrands using prescriptive unitarity. We find two possibilities for defining massless bubble coefficients. We can either match fixed massless bubble coefficients using well-defined singlet cuts, and the result is an integrand with improved behavior and affinity on these singlet cuts. Or we can use collinear contours to define the coefficients of these massless bubble integrands, and the result will reproduce the expected standard UV and IR structure. So let me conclude with some future directions and open questions. So at one loop, it's not clear which options is preferred, and we would like to test both strategies at higher loop beginning at 2 loop. And we will also, now that we have defined the loop integrands onshore, we would like to know if they can arise from any recursion relations. And third, we have discussed the integrands for n equals 1 and 2. In n equals 3, there are more subtleties like the massless bubble coefficients due to the presence of tadpoles and rational terms, which are integrands with no loop momentum dependence. And the open question there is, can we find a gauge invariant cut level definitions of the pure Yamil's loop integrands? And finally, we'll be interested in looking at if we can reproduce the n equals 1 and 2 super Yamil's integrands as differential forms associated with some positive geometries. And that's all I want to say. Let me finish here, and thank you for your time.
Sure. Thank you very much. We have time for some questions. Is there any questions from maybe the audience in UCLA or on Zoom?
Sorry, I didn't catch that. Is there a question there?
Is there any questions? So.
Anyway.
David has a question.
Yeah, so I'm just curious that a number of years ago, Ruth Brito and some of her collaborators showed how to extract this coefficient of essentially the mass or the wave function normalization for massive scattering. And the question is this procedure, is it the same procedure that you would get from the massless limit of what she was doing?
Yeah, we don't know. Yeah. Well, the thing is that here there is a tension between these two cuts. So you cannot make both of them at the same time.
I understand that, but
Just speak up so people with the world.
Yeah, we don't know. Yeah, that is a good place to look at.
Is there any other questions?
Maybe I can ask one. So can you comment more on like new observations for the integrand?
Oh no, I don't have much to say about this. This is future direction that we really haven't started investigating in greater detail.
Yes. Okay. Okay. So if there's no, if there's no more questions, maybe we can thank the speaker and then.
What's the last earlier work about?